I-4 Part 2 video on the indefinite integral and net change theorem. And recall that we have to memorize several general antiderivative forms, such as the ones you see in 6, 7, and 8. But I wanted to say one thing about Leibniz. Gottfried Leibniz, he was a philosopher, mathematician, and he was one of the founders of modern-day calculus. If you ever read up on the debate about who founded calculus, it was Isaac Newton and Leibniz, coincidentally, or at the same time, in two different locations. One of his favorite quotes is, "Everything that is possible demands to exist." And so really like that quote a lot. So if it's possible, it demands to exist. So we went over some of these, talked a little bit about general antiderivative forms, and then we worked example 1, found our answer with example 1 and the general antiderivative, and then we evaluated the indefinite integral. When we saw sine over cosine, we used trig identities to see that what sine over cosine squared really was just secant x tan x, which is a known antiderivative of then secant x plus c. So a known derivative of secant is secant tan, so that'll be the hint for you to look for when you're dealing with trig functions at this stage. So our next problem has to do with a definite integral, as I said. So we're going to evaluate the definite integral from 0 to 2 of x cubed minus 4x dx. So we're going to use a little fundamental theorem notation for this. So recall that we have f of b minus f of a is equal to the integral from a to b of f of x dx. So that is the fundamental theorem part 2. Remember, if f is continuous, then on the closed interval AB, we can integrate. So what you have here then is f of 2 minus f of 0. So some antiderivative evaluated at 2 and that same antiderivative evaluated at 0 is equal to this integral. So we take the antiderivative of x cubed minus 4x, and that gives us x to the 4th over 4, minus, then we have 4x squared over 2, and then we put a bracket on, and we say we evaluate that from x is equal to 0 to 2. So we get the following. So this we don't do anything at all with the left-hand side. We're just going to evaluate at 2. So here's our antiderivative in here. So we're going to say, plug in the 2, plug in the 0. So we're going to plug in the 2 to the 4th over 4, minus 2 times, remember the 2 and the 4 cancel, so that's just 2x squared. So we plug in the 2 times 2 squared. So I'm going to put parentheses around that part. And then we're going to subtract, because this part is f of 2. Now I'm going to do f of 0. Trivially so, it is 2 times 0 squared, just plugging in the values. So on the right-hand side, this all goes to 0. And then we end up with 2 to the 4th, or 16 over 4, which is 4, minus 2 times 2 squared, which is minus 8. So we get 4 minus 8, or we get a value of negative 4. And in this problem, explain your answer's sign. So we have the integral from 0 to 2 of x cubed minus 4x dx is equal to negative 4. So explaining the sign, and we did talk a little bit about area, so if you consider the area from 0 to 2, you notice it is below the x-axis, and therefore is a negative area. Okay, so it produces a negative area. So there's our answer, and let's move on to the next example. You can pause your video at any time or rewind to review. So find the exact value of the integral from 0 to 8 of x plus 5 cosine dx. So with this one, we're going to just take the integral. Now I could say remember, we're going to integrate, we're going to find the antiderivative evaluated at 8, and then we're going to subtract the antiderivative evaluated at 0. So we begin. We have x squared over 2. The antiderivative of x is x squared over 2, plus, then we have 5 times the antiderivative of cosine. The antiderivative of cosine is positive sine. And then our arbitrary plus c constant. So now what we're going to, oh, no arbitrary c. I'm going to take that off. And we're going to put a bracket instead. Recall that with the arbitrary constant c, it would cancel anyhow if we did include it. So x is equal to 0 to x equal to 8. So we get the following results. Let me move it over here a little bit. It's equal to then 8 squared over 2 plus 5 times sine of 8 minus, then we have 0 squared over 2 plus 5 times sine of 0. Now here's another example where 0 squared over 2 is 0. That's gone. 5 times sine of 0. Sine of 0 is also 0. So this whole expression goes to 0. So we end up with the following expression. We end up with 64 over 2, or 32, plus 5 times sine 8. Sine of 8 is not a regular or a standard angle that we would be used to, so we'd probably put it in a calculator to see what we would get. So let's do that. Put it in a calculator to see what the sine of 8 is. And so we get an approximate answer of 32 plus 5 sine 8 is approximately 36.9468. Now, the thing about this is it should be a positive area, because if you look at the area of this big, large section, that's a positive area. Here's more positive area. And then if you look, there's only one little section that's negative, so there's no way that your answer is going to be a negative value in the end. So we get an approximate big answer of 36.9468. However, one of the things that I have to warn you about is you're working with trig functions. Remember, you need to have your mode set in radians and not degrees. And sometimes you might forget to set it and you're going to get the wrong answer. So remember, with your calculator, let's just look at the mode button really quickly. So mode, always make sure you're in radian and not degree when you're dealing with trig functions. Okay, so take the time, maybe you want to put that function in and find your area using your second trace 7 keys. Okay, moving on to the next example. So now, example 5, evaluating the definite integral. It looks like we're going from 2 to 10, so we're just going to go ahead and evaluate this. In the back of your mind, you want to think, okay, this is going to be an antiderivative evaluated at 10 minus the antiderivative evaluated at 2. So the thing that I know here on this problem is we have a little rewrite to do. So what I'm going to do is I'm looking at this first. It looks kind of heavy, right? Like you're looking at it, you have a square root, you have a fraction, so there has to be some way to simplify it before you start. So you begin this and you just do a little rewrite. A little calculus, a little rewrite. Okay, so we handle this, we go, all right, this is now the integral from 2 to 10. So I'm going to split this up. I'm going to say 2t over t cubed plus, then I have t cubed square root of t, which I know I'm going to combine. I'm going to make that t to the 1/2 right now, over t cubed. It's kind of nice. Minus 3 over t cubed. I'm going to take this extra step so that I can simplify, even though many of you would have canceled at this step. Canceling the t cubes. Now, I'm going to cancel the t here and make this a 2. So let's see what we get. We get that this integral is the integral from 2 to 10, then, of 2t to the negative 2, plus then we have t to the 1/2 minus 3t to the negative 3rd power dt. So our integrand is all ready to go. So now recall that you're going to use this power rule. If you have a power x to the n dx, then you're just going to use the power rule x to the n plus 1 over n plus 1. So if it looks like I have fractions
like 3 over t cubed, I'm going to want to write those using negative exponents instead of keeping it as 3 over t cubed. So, looks like we're ready to go then. Okay, now this is a definite integral. So, here we go. So we end up with 2. Now remember, we're just going to keep the constant, and we're not going to split up the integral this time. We're going to keep with it everything together in one integral. So we have t to the negative 2 plus 1 is negative 1 over negative 1 plus, moving on, t to the 1/2 plus 1 is t to the 3/2 over 3/2 minus 3t to the negative 2 over negative 2. And then we, of course, will evaluate that from t is equal to 2 to 10. Continuing with this expression, then I'm going to fix up each of the terms, and this would then be 2, so it would be negative 2 over t, negative 2 over t, negative 2 over t, and that would be plus, this is going to be a 2 t to the 3/2 over 3. Then I have, what do we have here? Minus becomes a plus because you have the 2 negatives. And then we get 3 over 2t squared. And then we're going to evaluate that from t is equal to 2 to 10. Okay, evaluating from 2 to 10, then we're going to start plugging in. And this, I don't know that they would have a problem that's this involved in the AP Calc multiple choice without a calculator, but it's not really too bad. And we have the time here, so I'm going to move this equal sign over here to just have a little bit more room. So equals. Now we're going to plug in 10. Remember that what we're doing is we're saying f of 10, the antiderivative evaluated at 10, minus the antiderivative evaluated at 2. So we're going to first plug in 10, so we get negative 2 over 10, plus then we have 2 times 10 to the 3/2 over 3, plus 3 over 2 times 10. Okay, that's 10 squared. And then we're going to subtract the evaluation with 2, so we have negative 2 over 2. Plus, we have 2 times 2 to the 3/2 over 3. Plus, then we have 3 over 2 times 2 squared. Okay, let me make sure we have everything plugged in all right. We have negative 2 over 10 plus 2 times 10 to the 3 is 3 over 2 times 10 squared. That's f of 10 over here. So, and then f of 2, let's make sure that we have everything plugged in right. Negative 2 over 2 plus 2/3 times 2 to the 3/2 plus 3 over 2 times 2 squared. Okay, so now we're going to simplify this expression. Ooh, so there's a lot involved here. Either use a calculator or get things straightened out here. I'm going to leave that up to you. But the answer that we get for this is then I get 19.63 using a calculator, 636,233 for a final answer. So we know that this thing is equal to the integral of from 2 to 10 of 2t plus t cubed times the square root of t minus 3 all over t cubed dt. So that's your answer, and like I said, I'll let you go through some of the math to double check that. All right, that's it for this video, and we'll be back with the next video, video number 3, in section 5 for the net change and indefinite integrals.